Hello, my name is Randy Wilharm, and I will be telling you about the strange phenomenon of neutron stars. Neutron stars were first theorized by Fritz Zwicky and Walter Baade in 1934 after doing work in the new field of quantum mechanics. They also had interest in astronomy, specifically with the phenomenon of supernova. They wondered what occurred at the core of supergiant stars right when they exploded into a supernova. Using new knowledge gained from discoveries in quantum physics, they were able to work out the immense energies and pressures found at the heart of a supernova would create an extremely dense star with very high gravity, a very low magnetic field, and would produce unique patterns of radiation. However, it took 33 years for such a star to be discovered. In 1967, Jocelyn Bell discovered a radio signal that pulsed at 1.3 pulses a second. This had never been observed before and fit no known source or phenomena, so she named the new object a pulsar. After checking all other possible sources, she realized that this could fit the prediction of Zwicky and Baade to be a neutron star. To be sure, she looked for other pulsars at the center of known supernova remnants, such as the Crab Nebula, and there she found more pulsars. This was conclusive evidence that her new discovery was indeed a neutron star. So what is a neutron star exactly? Neutron stars can be characterized by four unique and identifying properties. They must be small, usually around 20 kilometers in diameter, very dense, with a mass usually around 1.5 times the mass of our Sun, have a very strong gravity, in which the escape velocity is typically around half the speed of light, and have a very strong magnetic field. The magnetic field creates the distinct radiation due to its interaction with charged particles entering as well as inside the star itself. As discussed before, neutron stars are formed from one of the most violent phenomena in the universe, supernova. Stars like our Sun are not large enough to produce supernova at the end of their life and will eventually form white dwarfs, as shown by the loop on the left. However, stars that are more than 10 times more massive than our Sun will go supernova at the end of their lives. In the process of the explosion, the core of the star is compressed so tightly that the electrons and protons in the atoms of the core combine to form neutrons, leaving a star made entirely of neutrons, which is where the name neutron star came from. If that star is too massive, though, the pressure in the core is so strong that a black hole is formed instead of a neutron star. So then what's the difference between a pulsar and a neutron star? Well, a pulsar is a type of neutron star that emits radiation on one axis that rotates around a separate axis, creating the pulsing signal observed on Earth. Pulsars are the easiest to detect of all the types of neutron stars because of their distinct radiation pattern. While most celestial objects rotate at rates on a scale of days to years, pulsars rotate at rates in the seconds to milliseconds. With so much mass rotating at such high speeds, there's a lot of energy contained in a neutron star. There are also two different types of pulsars. The first are radio pulsars that produce radio waves as their radiation. They are the more typical pulsars and relatively not very energetic. The radiation comes from the angular momentum of the pulsars, so radio pulsars eventually slow their rotation. The other type of pulsars are X-ray pulsars, which emit radiation as much more energetic X-rays. These pulsars are formed when material enters into the star and is accelerated in its magnetic field. This adds energy to the radiation, causing the X-rays. Because of the high energy radiation, X-ray pulsars only stay in this state for a relatively short time, about 10,000 years. So what do we know about neutron stars today? We have found about 2,000, mostly being pulsars. They are difficult to find for many reasons. They rarely emit at visible frequencies and often occur very rarely. Additionally, they have relatively short lifespans. And last, if its rotational axis never points at Earth, they are almost impossible to detect. The closest known neutron star to us is located 250 to 1,000 light years away in the direction of the Little Dipper. This video was made for a project for PH 1600 at Michigan Technological University. Thanks for watching.